I'm going to be tackling some of the physics and mathematics problems in this amazing book from 1977 titled Geometry, Relativity in the Fourth Dimension by Dr. Rucker, who is a writer, mathematician and painter. This book introduces the reader to the concepts needed to understand Einstein's special and general theories of relativity. The book leans more towards special relativity than general relativity, but it's unique in that it introduces such concepts as non-Euclidean geometry and higher dimensional geometry in a painless and pedagogical way. You can read Rucker's book for free online at the link on the screen, which I will also provide in the description of this video. At the end of each chapter of the book, Rucker provides a series of conceptual and mathematical questions on the content that's been covered. In this video, I will answer the questions found at the end of the first chapter on the fourth dimension. In question 1, we are asked to complete this table, which lists the number of vertices, edges, faces and solids for a point, segment, square, cube, hypercube, which is a cube in 4 dimensions, and a hypercube, which is a cube in 5 dimensions. In order to solve this problem, we can use a neat trick as follows. We take x plus 2 to the power of n, and we can expand this into the familiar form of a polynomial, which looks like some coefficient a times x to the power of 0, which is 1, plus some coefficient b times x to the power of 1, plus some coefficient c times x squared, plus some coefficient d times x cubed, and so on. The values of a, b, c, d, etc. will depend on the value of n, and in this case n is the number of dimensions for our geometric objects. I've written an ellipsis here because we could keep on writing terms with higher powers of x even if the coefficients are equal to 0. As we shall see, for an n-dimensional cube, the coefficient a represents the number of vertices, b represents the number of edges, c represents the number of faces, and d represents the number of solids. For n equals 0, we have x plus 2 to the power of 0 is just 1, which can be written as 1 times x to the power of 0 plus 0 times x to the power of 1 plus 0 times x squared plus 0 times x cubed, and so on. What this tells us is that a zero-dimensional cube, which is just a point, has one vertex, no edges, no faces, and no solids. For n equals 1, we have x plus 2 to the power of 1 is just x plus 2, which can be written as 2 times x to the power of 0, plus 1 times x to the power of 1, plus 0 times x squared, plus 0 times x cubed, and so on. What this tells us is that a one-dimensional cube, which is a line or segment, has 2 vertices, or vertexes, 1 edge, no faces, and no solids. For n equals 2, we have x plus 2 to the power of 2, which is x squared plus 4x plus 4, which can be written as 4 times x to the 0, plus 4 times x to the 1, plus 1 times x squared, plus 0 times x cubed, and so on. What this tells us is that a two-dimensional cube, which is a square, has 4 vertices, 4 edges, 1 face, and no solids. For n equals 3, we have x plus 2 to the power of 3 is 8 times x to the 0, plus 12 times x to the 1, plus 6 times x squared, plus 1 times x cubed, and so on. What this tells us is that a three-dimensional cube has 8 vertices, 12 edges, 6 faces, and 1 solid. Hopefully by now you understand the process. Now we're going to get into the fourth dimension and even higher dimensional geometry. For n equals 4, we have x plus 2 to the power of 4 is 16 times x to the 0, plus 32 times x to the 1, plus 24 times x squared, plus 8 times x cubed, plus 1 times x to the 4, and so on. What this tells us is that a four-dimensional cube, also known as a tesseract or hypercube, has 16 vertices, 32 edges, 24 faces, 8 solids, and 1 hypersolid, which is a four-dimensional solid. Now, it's difficult to imagine something with 8 solids, let alone a hypersolid, but in the next question we will attempt this visualization. If it's hard to imagine, what use is it? Well, as described in the book, it's sometimes helpful in physics to think of time as a dimension, in addition to the 3 spatial dimensions we are familiar with. Thus, instead of just thinking about 3D space, we can think about 4-dimensional space-time, which is central to Einstein's theories of relativity. But let's not stop there. For n equals 5, we have x plus 2 to the power of 5 is 32 times x to the 0, plus 80 times x to the 1, plus 80 times x squared, plus 40 times x cubed, plus 10 times x to the 4, plus 1 times x to the 5, and so on. And what this tells us is that a 5-dimensional cube, also known as a hypercube, or more simply just a 5 cube, has 32 vertices, 80 edges, 80 faces, a whopping 40 solids, 10 hypersolids, and 1 hypersolid. So if you thought it was difficult to imagine a hypercube with 8 solids, try imagining a hypercube with 40 solids. Putting it all together then, this is what our completed table looks like. Now in question 2, we are asked to locate all 8 cubes that form the 8 solids of the hypercube in the figure. This figure, Rucker tells us, comes from a book published in 1913 titled A Primer of Higher Space by an architect named Claude Bragdon. Of course, this figure is not in 4 dimensions, in fact it's not even in 3 dimensions. It is a 2-dimensional representation of the 3-dimensional cubes that make up a 4-dimensional hypercube. In reality, whatever that means, the 3-dimensional cubes would be connected through the 4th dimension, but since that is impossible to draw on paper, Bragdon uses diagonal directions to represent the 3rd and 4th spatial dimensions instead, which are not truly orthogonal, but that's just a limitation. It is challenging at first to visualize all of these cubes, so I will illustrate each of them in pairs with color shading. The first cube is here on the center left in red, and its partner is here on the opposite side. The third cube is at the top left in blue with its partner opposite. The 5th cube is down here on the bottom left in green with its partner opposite. Finally, and I think these are the trickiest, we have the 7th cube at the top in yellow and the 8th cube down at the bottom. Thus, Bragdon's figure contains 8 cubes representing the 8 solids of a hypercube. Question 3 asks how many hypercubic meters of hypervolume there are in a hypercube, each of whose edges are 2 meters in length. Well, just like in question 1, we're going to start with lower dimensional objects and work our way up. In 1 dimension, a segment or line has length L. In 2 dimensions, we define the area of a square as A equal to L squared, that is L times L. And in 3 dimensions, we define the volume of a cube as V equal to L cubed, that is L times L times L. You may have noticed a pattern here, whereby we multiply by another factor of L for each dimension, and indeed we can repeat this up to 4 dimensions, whereby the hypervolume of a hypercube is H equal to L to the 4th power, or L times L times L times L. Thus, we can set L equal to 2 meters, and taking 2 meters to the 4th power gives us 16 hypercubic meters of hypervolume. Remember that we have to take the units to the 4th power also. Now, the original question in Rucker set the edges equal to 2 feet, in which case the answer would be 16 hypercubic feet, but for the sake of science, I've replaced the original question with the metric system. The final mathematical question for Chapter 1 of Rucker is question 4. Which presents the formula for the hypervolume of a hypersphere of radius r as the integral from minus r to r of 4 over 3 times pi times the square root of r squared minus x squared to the 3rd power times dx. And we are asked where this integral comes from. The explanation I will present is not mathematically rigorous. I will skip over the formalism, but I hope it is intuitive. Once again, let's drop down to the lower dimension and go by analogy. The formula for the volume of a 3-dimensional sphere of radius r is the integral from minus r to r of pi times the square root of r squared minus x squared squared times dx. If we let tilde r equal to the square root of r squared minus x squared, we see that the integrand is pi times tilde r squared. But recall that pi r squared is the area of a circle of radius r. So one way of thinking about this is that the integrand represents the area of a circle, and this integral is like raising the area to a higher dimension, namely the 3rd dimension, in order to obtain the volume. So with this line of thinking, let's go back to the original question. We can again let tilde r equal to the square root of r squared minus x squared, so that the integrand is 4 over 3 pi times tilde r cubed, which is simply the volume of a sphere. So one way of thinking about this integral then is that the integrand represents the volume of a sphere, and the integral is like raising this volume to the fourth dimension, which then gives us the hypervolume. We can see this increase in the power of r more clearly by evaluating the integrals to obtain the n-dimensional volume of a sphere in n dimensions, which is called an n-ball. I don't come up with the names. Again, for a circle, the area is pi r squared. For a sphere, the volume is 4/3 pi r cubed, and for a hypersphere, or 4-ball, the hypervolume is 1/2 pi squared r to the fourth power. There is in fact a closed form expression for the n-dimensional volume of an n-ball of radius r, which is pi to the n/2 times r to the n divided by gamma of n/2 plus 1, where this gamma is the Euler gamma function, with gamma of n equal to n minus 1 factorial for positive integers n.